Ladies and gentlemen, my name is Drew Berry. I'm one of the animators who will be presenting some work tonight. To fill in some time, just a few minutes, I'm actually going to present you something else. It is sort of a light entertainment. And it is a mixing of science and art, so you can absorb it and take what you want from it. It was actually I've been working in this field about almost 20 years now, and one of the things that happened just over 10 years ago was that I found that there was a huge demand in the public for art, for science in art. And so what I'll do is present just 2 minutes of a project of a science and art festival. Vivid is the well-known one in this region for having projections, architectural projections on buildings. But Melbourne has a comparable one, which is White Night Melbourne. And I'm just going to present just a minute or two of that effort we did last year. So it looks like we have our main guest here. Oh, go ahead and play a bit of this. Now this was for purely an art festival. The room itself is the State Library of Victoria's reading room. So the dome itself is 35 meters across, and we wanted a projection inside this building. And the dome itself, very geometric forms, it was very reminiscent of viral powder coats to me. So I was thinking about that as an idea. And so what we ended up doing was 8 different viruses that have huge impact on human society. And all of this is real data. The virus itself is blown up 1 billion times. This artwork is called Virus 1 billion times. The real virus capsid from X-ray crystallography. And if it's a DNA or an RNA virus, we had the DNA or the RNA crawling around the walls. During the time of each virus had about 2 minutes. We also put little factoids around the walls, like the number of people infected in the room by this virus, or the number of genes in this virus, or the historical context of, for example, influenza killing 5 million people 100 years ago, and now only merely killing about 300,000 people per year. So those sorts of ideas of real science and trying to so the idea of the festival was 1 night only. And we we're at capacity the entire night. 5 a.m. the next morning, there was still a 27-minute queue to get in. But it was really tremendous and really encouraging for me to be able to sit amongst the audience. We constantly had a new flow of people going through, but the amount of intelligent conversation that was going on with all the public, from young kids, teenagers, 20-somethings, about viruses and DNA and the impact of this on them. I have to admit that herpes was the most popular one. Whenever it came up, people would go, "Whoa, herpes!" Lots of people had very familiar experiences with herpes and had many stories to tell, but there was typically someone who knew what DNA was, what RNA was, and would start a conversation in all these different groups during the show. So it really was a fabulous event, a big spectacle of science as art. And what I found is this is not only emerging early in the last 10 years, a tremendous demand out there for big science festivals for science as art. And with that, I believe we'll switch over to Aiden Chubb. So.
All right, there we go. Okay, welcome, ladies and gentlemen. I'm glad you could all make it to the premiere of the new animations that we created in the VizbiPlus project. This project was partially funded by an Inspiring Australia grant and was a collaboration of CSIRO, the Walter and Liza Hall Institute in Melbourne, and the Garvan Institute in Sydney. And as part of that project, we trained 3 scientists to become animators and basically create little clones of Drew Barry, whom you just heard from. He does such fantastic work, and so we thought it would be a shame to not multiply those kinds of skills. And so he served as the mentor in the project that resulted in the production of 3 animations last year, and then there'll be 3 more this year, 2 of which are ready today, and we're about to present you later on tonight. Our first speaker, however, is somebody who is a fantastic champion for science, the best one I can imagine. It's Australia's chief scientist, Professor Ian William Chubb.
Thanks, Christian. Ladies and gentlemen, let me begin by apologising for being late. As we say these days, it was my fault. I had difficulties. But I'm really pleased to be here because I think this is one of those mechanisms by which we can make the importance of science, but probably even more importantly in one way, the awesomeness of science available to, accessible to the public at large. And I think that's an important thing for us to do. I am known to be moderately critical of the fact that over the years and decades, and from the time that I can remember when I was myself a young scientist at the bench, I don't think that we've done enough as scientists to communicate well enough with the public on whose support we depend. And I guess as I've got older and operated in different spheres, then I want to leave you in no doubt, if any of you have any doubt, that if we want politicians to respect, to look after, to support science in the way that we would like to see that in this country, then we have to get the community advising the politicians, not absent-mindedly, as they might do when they vote, but in reality, advising our politicians that this is a particularly and critically important part of Australia's future and the sort of future we want to build, by contrast to the sort of future we want to let happen. Now, for those of you who don't know what a chief scientist does, I'll give you 2 sentences on it. I travel a fair bit around the country, and I give a lot of speeches. Last year I gave 110 speeches from one end of the country to the other, north to south, east to west. And a lot of those speeches were to completely different audiences on lots of completely different topics. So it's an interesting life and an interesting role. But what that does is it lets me hear from people in all those places, from all sorts of different backgrounds, what they think about science. So I hear from scientists who think it's wonderful. I hear from scientists who get depressed by what they see to be inadequate support. I hear from scientists who can't wait to tell you about the latest thing that they did and show you the latest thing that they did. And some of that is really, and quite simply, spectacular. So I've got a pretty fair view, probably did have it, but reinforced view of how science is seen by people inside science. We understand it, we understand the complexity, we understand the ambiguity that you get in the work, particularly in biomedical sciences. We understand probabilities, we understand evidence, we understand skepticism, we understand scrutiny. We know that we have to put our results and our evidence out there and have it stand the test of the scrutiny of our peers. And when that happens, we feel really good about that. And we know our peers like us, but we've got to get the rest of the community liking us as well, and much more comprehensively than they do now. Some of my speeches are to business groups, to groups in other sectors of the Australian economy. Some people who want to use science, but don't necessarily fully understand what science is. I speak to a lot of members of the community who are anxious about things. So they're anxious about climate change. They're anxious about some of these viruses. They're anxious about it. They're anxious about things. And we talk about how science can, at least Australian science, can contribute to the solutions that the world needs if we're going to make this world a better place for us all. So I see people who would like to understand more about science, have a higher level of science literacy, if you will. And then I talk to people who, for a variety of interests, don't believe too much of what scientists say, unless it impinges directly and positively on them. So we see some people in some sectors of the economy, for example, being deeply critical of climate science. But much worse, they are deeply critical of climate scientists. And they declare to be frauds. There's a Roman Englishman who travels around the world who suggests that a number of them should be put in jail, simply for providing evidence that some people don't like and don't want to hear. And it's up to us as a community, both scientific and general community, not to accept that. And not to accept it with a passion, not to accept it because we know it to be wrong, not to accept it because we just don't think that this ought to be a way in which science and the positive effects of science, the impact of science on all our lives should be diminished by people who are running a different agenda. But to achieve their agenda, they have to somehow suggest that science is wrong. So we know that one of the things that we have to say and to explain to people is in the way that you just saw and will see. It has to be attractive to people, it has to be accessible to people. And it's got to assume the sort of technical talk that we will use when we speak to each other. It's actually got to be accessible in a completely non-patronising way. I think that one of the things that we have learned is that it's very easy to be patronising. It's very easy to think you know everything, and in fact you know a bit about something. But it's also on the receiving end of that, not something that people who think about it already regularly accept. And we know that in terms of the research that we do, leave aside the teaching that we do, but the research that we do, but a lot of that research will have benefits for our community, benefits for our society, which are not always predictable, and which actually require people to have patience. When good work will eventually be, may eventually be, translated into issues, facts, things, substances, discoveries that will make us better as human beings, healthier as human beings. But science has got to work in tandem with the community to achieve those outcomes. Gone are the days, I'll turn the phone off, that somebody should have said before I start, please make sure your mobile phones are turned off. Sorry about that. But we've got to get the community to accept the fact that this process of science, this method of science is really important to our advancement. And we've got to work with the community to do it. So I'm only going to quote two things at you tonight, but two of them from the same person. When Tony Blair was Prime Minister of the United Kingdom, he gave a speech to the Royal Society of London and he said, and I quote, "Science doesn't replace moral judgment. It just extends the context of knowledge within which moral judgments are. It allows us to do more, but it doesn't tell us whether doing more is right or wrong." And I think it's important for scientists to understand that it lets us do more, but it doesn't necessarily tell us whether doing more is right or wrong. That is a community issue. Blair said in the same speech, the benefits of science will only be exploited through a renewed compact between science and society, based on a proper understanding of what science is trying to achieve. So another way of putting that is to explain to the community, explain to society why we do what we do. why it's important that we do it. And we do it all the time. We just don't wait until the newspaper headline of breakthrough can be published by somebody which lasts 12 hours and then the ink begins to run. It's actually about something which endures. And it is about something where the society understands why, as they walk along the path with you, you're doing what you're doing. Sometimes it will just be to increase knowledge. Sometimes it will be to use and to apply knowledge. All of those sorts of things are very important, and very important for us to take the community with you. So, ladies and gentlemen, I think it's for me, it's a pleasure to be here to participate in this launch. I think that what we've just seen, and probably what we will see, is an important mechanism, an important device to get proper science, really informative science, information about science, through to a very large number of people, many of whom will choose not to study science, or not to be scientists had they studied science. But we're increasing the level of understanding of the population. And that can only do us all good. Good as a population, good as a bunch of scientists, good as a government if we want to persuade the government through the community that science is important to our future. All of those sorts of things. And to make sure that science gets the proper place, the place that we would all like to see it, and that through science we do indeed make the world a better place. Thank you.
Yes, so up next is Drew Barry. He works at the Walter and Eliza Hall Institute and has been creating wonderful animations there over the last 15 years. For his work, he received way too many awards for me to mention right now, but one of them was a BAFTA, another one was an Emmy, a third one was a MacArthur Fellowship, otherwise known as the Genius Grant. So, anyway, I let him show you more of his work, and that'll do a better job than me talking about him. So, please welcome Drew Barry.
It's a great pleasure to be here and be able to present to you all. I represent the first of the animators that will be biomedical animators that will be presenting to you today. And I'm of the old generation. I'm from last century when I began this kind of work. What this current project, the VizbiPlus project, has enabled me to do is to contribute to training the next generation of biomedical animators. When I began back in the 90s, there was already tremendous revolutions underway with medical research, and a collision with tremendous revolution and combined with tremendous revolution in technology, making our advancement of knowledge and our frontier of understanding just explode outwards. And with that, there was an ever-increasing need to explain to the public the discoveries that are being made so that they can make informed decisions or an informed debate about the sorts of changes that were underway and the sorts of changes that are likely to be happening because of the technology. So that's where my work stepped in. All of the animators you're going to see are all credentialed scientists from background. I'm a microscopist from Melbourne University originally, but we all transitioned then into biomedical communication, biomedical art. This idea is nothing new. Being humans, we've always used pictures to sketch out ideas, to think through something, but also to convey to some other people what it is you're thinking and discovering or seeing through a microscope or a telescope. The work was originally meant for television to help convey complex topics like cancer discovery on a news bulletin. So you come home at the end of the day, you're tired, your kids are screaming, you're trying to prepare dinner, and then the news bulletin comes on and you're trying to explain what a discovery about cancer molecule or perhaps diabetes or what malaria, new discovery about malaria, and you only have 10 or 15 seconds to convey that visually. And that's where originally the idea for my kind of work came from. Now, because of the transformative nature of media today, the internet is obviously a huge and vast area of potential for reaching massive audiences. But now we also have massive markets and audiences, people hungry for this kind of information. At museum exhibitions and science centers like this one, at art festivals like I briefly showed you before, but also quite clearly with education. And that's, I'm going to present a little bit of my work that we finished end of last year, which is aimed at high school education. I mean, education is the obvious area of tremendous need for explaining things to students, to high school kids, and getting them so they understand the topic. But more importantly, before that, is engaging them, getting them excited, getting them motivated, getting them asking really intelligent questions. In order for that to happen, they have to have a sense of what the science is about, and just an idea of what that world represents. So one of the, this project called Life on Earth, which it took us 2 years to raise the money and about 2 years to produce the work. It's a collaboration with E.O. Wilson, a very well-known biologist from Harvard University. He was our lead author. A team at Harvard Medical School, and also a team in Melbourne at Walter and Eliza Institute, all creating this content. What we want to do is revolutionize the nature of what a textbook is. Instead of these $150 printed textbooks that are already a couple of years out of date by the time they get to students, and also limited by the nature of what a textbook is, just a printed sheet, you have images, you have text, that's about it. We wanted to open up to all the possibility and potential of electronic media, and that's what we've done. This book, this textbook is complete curricular biology, and it's available for free. It's going to be updated automatically online. It also has all of the wonderful books behind the scenes for the teachers to see how their students are performing, where they're spending time in the book, maybe where they're getting stuck, and getting feedback from multiple choice questions at the end of each chapter. So I'm going to be playing it from my iPad here. It's designed specifically for the iPad. The textbook is split over 7 volumes. It's sort of grouped for work topics that students are working on together. And I'm just going to step into one of these books and just briefly demonstrate what it is, what a digital textbook is like. So we're stepping into this particular volume. I'll step out. It is a textbook. We couldn't move the goalposts too far. We had to create something that the teachers would expect, not to confuse them too much about the nature of what this material is. So it is a textbook. And what I'll do is step in. You step into the chapter. And being a textbook, you do look at the images, you read the narrative of the text, and it leads you through the material. And advantages, you can zoom into images and have high resolution detailed images. That's all sort of what you expect. There are other things many actually different experiments, interactivity that we did. This is just one of them, where you're reading the flow of the text, and it's trying to, this figure is trying to give you a sense of the scale. How big are cells? By relating it and connecting it to our familiar experience of the world. So you step into this particular figure, and it's not just a still image. So the student is on the iPad. They touch and they drag and they interact directly with the image. And what the idea is, you just start to zoom in and you start to explore the human hand at different scales. So here's a centimeter. You start to get closer to the skin. You start to see the layers of tissue. You start to see sweat glands. I'm going to skip ahead. We zoom through all the various layers of tissue down to a millimeter and down to 10 micrometers. And here is a cell. So the idea is the students can play with this as much as they want. They zoom in now, and they get a sense of all those powers of 10 all the way down to a cell. Then this cell, we've reconstructed in high resolution, all the different structures we know about inside of that. So this becomes the hub cell for the rest of the chapter, where you keep revisiting this motif over and over again, this cell here, and explore the different structures inside of it. I'm just going to pick a couple of examples, different favorite organelles. The first one is, if you've done high school biology, maybe familiar because it's a funky name, the Golgi apparatus. And this is a little short linear video, but I'll talk about afterwards the sort of science and data that went into this.
The Golgi apparatus is a stack of flattened membrane discs that process newly made proteins and lipids from the endoplasmic reticulum. During their journey through the Golgi, proteins are modified and packaged and then directed to their final destination within the cell or to the plasma membrane for secretion.
All right, pause it just there, back to the book. So this structure here is very dynamic, many layers of membranes. This particular visualization was developed from and derived from a high resolution reconstruction of a single cell within the pancreas. that's producing insulin. So on the left-hand side, for the scientists in the room, is the edge of the nucleus and the endoplasmic reticulum, another organelle structure. And then you have, it sort of progresses from the left to the right, the maturation of the Golgi. And essentially, all sorts of molecules go through the system and get prepared in various ways for either in jobs inside the cell or for secretion into the bloodstream. And this one is from a beta cell, a pancreas cell that's producing insulin. And these large vesicles on the right-hand side, those sort of spherical blobs, are inside of them. There's a giant crystal of pre-insulin that's about to be ready to be released to the bloodstream. So this was the way the data was constructed for this particular animation was they took out a single cell and sliced up to 1,000 thin slices and then stepped through by hand and worked out the structure of the organelles inside that cell. So that's the overall structure. But then, which is typical of all the work you're about to see, it combines many forms of data all together in one visualization. There's also the dynamics of this visualization. It is what was derived and combined from time-lapse microscopy of Golgi and how they evolve and how they move. So multiple forms of data brought together in one. Another similar organelle is the mitochondria, or similar in its dynamics or its dynamic behaviors. And I'll go ahead and play this one.
The major function of the mitochondria is to provide the cell with energy in the form of the energy-rich molecule ATP. Mitochondria are dynamic and come in a variety of shapes and sizes, fusing and dividing to suit the changing needs of the cell.
Just a comment on about the narration, and it is in my voice. All the animations here all have the narration. The narrator is the person who created the animation. But beyond that, they're the person who did went through all the literature, gathered all the forms of data. They tend to understanding directly because they can navigate. They're trained as scientists. They can navigate the language. They know what they don't know, and they know how to find out. They know how to search the literature and find all the details they need to build a visualization. Find out what our current state of understanding is. So they're the person who did that research. They then took in the data, were able to examine it, and then reconstruct the visualization. And they also designed the narrative flow and the visual flow of how to tell the story. So one person does the entire job. It's usually broken into 5 or 6 different jobs in a company to produce this kind of content. I'm very adamant. It has to be the person pushing the pixels around on the screen has to be the content expert as well. We don't need a scientist leaning over their shoulder explaining complex jargon, and they have to try and typically if you speak to an animator, they're very, very good at they're dealing with high-end technology, but it's not the area of familiarity, it's not the language that they're used to speaking, it's the scientific jargon. All of us who have a science background are comfortable with that. We're comfortable with not understanding, and we're comfortable with then finding out the answers to what we don't understand. So, or at least finding out what's possible in the literature. And it's always fragmentary, there's always gaps, and then we make, where there are gaps, informed speculations, based usually on descriptions in the literature about what scientists, the actual experts, think is going on. So I'll play one more animation. Now this one is a lot. It's a lot of science, too much. But it is actually for the students because they're in, I forget which volume this is. They've already encountered a lot of these animations before in other contexts. And this is bringing many forms of data together. But I want to show you the molecular visualizations that we're able to achieve nowadays, which for me is the most extraordinary thing. When 10, 12 years ago, when I was doing similar sorts of work, I had to have $80,000 SGI computer, $40,000 of the software, and I already had 5 or 7 years of practicing to create this sort of content. Nowadays, that's gone. On a typical laptop or even an iPad, primary school kids can play around with molecules and with real molecular dynamic simulations, and they can play with it, and it's entertainment to them, but they're learning so much about how these things are operating. And now kids with laptops can open up and then download the software for free and then get going. And they are, and they're learning stuff in school. It's a whole new culture of expression of using this kind of technology. But so if the science of this particular animation gets a bit, it is too much and it's very quick, then just focus on the visuals and hopefully you'll at least get something from seeing the molecular images and molecular machines in action.
The cytoskeleton is a dynamic network of filamentous proteins that extends throughout the cytoplasm, forming the struts, cables, and girders that give the cell its shape, internal organization, and mechanical support for movement. There are several types of protein filament, each built from subunits that rapidly come together or break apart, allowing these elaborate structures to be assembled and dismantled wherever they're required by the cell. Microtubules are stiff hollow tubes that anchor other organelles and serve as tracks that guide the movement of vesicles and other cell components. Actin are thin, flexible filaments that form cross-linked bundles and branching networks. Actin is particularly important for cell movement. They are central to the contractile engine in muscle cells and provide mechanical force for cell movement at the plasma membrane.
So it's an intense amount of science, but the kids are getting engaged, excited by these mechanisms, and they're getting this sense of what the molecular world is like. I reiterate, all of this is derived from real data. We do not make stuff up where we can avoid it. It's only filling the gaps where we do have to speculate, but we do it in an informed way. We do use artistic tricks to make sure you're looking at the right part of the screen and make sure the narrative is comprehensible. And we use color and sound, obviously, to make this stuff engaging. That's all part of the artistry of this, of making this work well in a communication sense. Anyway, I'm going to hand over now. You've got a whole bunch more animations to watch, the main event now. All of the work you're going to see derived in the same, are built in the same way. Research, playing with the models on the computer screen, and devising a way to tell the narrative directly. It was been my great pleasure in the last 18 months during the duration of the VizbiPlus project to work with these scientists, biomedical animators, and to help mentor them with developing this kind of work, because there is a tremendous need, it's overwhelming need for many, there's so many stories to be told, so many avenues, so many different markets to put this kind of content. So we need many more people to be doing this kind of work. So I'll hand it back to Christian. Actually, Mike is speaking next. So I'd like to introduce Dr. Mike Lawrence from the Walter Liza Institute. He runs a lab focusing on the insulin receptor and how the insulin docks into the molecule. So thank you.
Good. Thank you. It's a pleasure to be here because my work became the subject of the video you're going to see shortly. This project involves how does insulin bind to the cell surface and send a message into the cell to tell that cell to take up glucose. That's what I'm studying. So insulin itself, insulin was discovered in the early 1920s. Within a year or so, it was injected into patients successfully to treat type 1 diabetes. But it took a long time after that to make much progress understanding what insulin was actually doing. And in the early 60s, the structure of insulin was determined as three-dimensional structure. I think it was the seventh protein to have a three-dimensional structure determined. That was the 1960s. To work out the structure of the receptor and how insulin binds the receptor took a little longer. And it was 2 years ago, 2013, that we managed to achieve that. So I'm sure what I put up here is our figure 1 from the major paper that we published that illustrated this work. And you'll see straight away that this is not exactly what you want to show to the public to illustrate the science. It's a wonderful thing to have as figure 1. It represents the culmination of almost 20 years of endeavor of a project that started, had its genesis in CSIRO. So the question is, how do we communicate that? Well, the day after the paper came out, I was inundated with requests from the press and TV to talk about it to the public, and there were many, some more successful than others. But the sort of thing that was really always alarming to me is headlines of this sort. And this was the next day in the Australian. Diabetes may soon not need to use injections for the insulin. Diabetics might not soon need to use injections for the insulin, which is completely the wrong story. But the papers were insistent that this was part of the story that I had to tell. Well, maybe that was true. Maybe that is where our science would go. I saw a whole number of other avenues into which it could go, and maybe this was one of them. But it's the sort of thing, and the problem that we have in communicating science to the public is, as Professor Chubb said, they want the headline, they want the graph, and then it will disappear. So we do need this extended message. And I was therefore delighted when Maja came to me and said that they had funds to produce a video regarding my work. And it's been a pleasure to work with Maja and with Drew, and to watch the skill that they brought to bear. That in a sense I could step back, I could interact with them, but I was confident that they would be doing the right story, as we mentioned, through their own scientific expertise and the ability to bring the story together. And in a sense, it would be great if that story is going to persist. We don't want it to just end up something in the paper that is one day. And also, the thing that we as scientists need is we need a continuum of that type of work, not just something that emerges perhaps a bit later that our work becomes encapsulated. It would be really beneficial if we could work with animators throughout our scientific journey, so that when something like this does emerge, we're ready to go. That to me would be absolutely tremendous. I don't have the time to do it. I'm not going to become an animator. So in a sense, I'm looking to you to be able to fill those gaps. So let me hand over now to Maja, and she'll tell you about the video that she's created. Thank you.
Okay, so I'm here today to launch the second part of two animations to do with type 2 diabetes. So I'll just start with a little bit of background. In a nutshell, it's basically the ability to control blood glucose because of disordered insulin secretion. And what is insulin? Insulin is actually the hormone produced by our pancreas that controls blood glucose. So with those two ideas in mind, type 2 diabetes consists of two main components. There's an inflammatory component, which damages the pancreas, eventually leading to decreased insulin production. And there's also an insulin resistance component, in which the insulin signal is not sent into the cell. So the cells don't take up glucose signals as an empty source. So on to the official launch of the second animation. It's about the insulin receptor and type 2 diabetes. So it describes the role of the insulin receptor, and it focuses particularly on discovering that my colleague about 2013 in his lab, which actually looked at how the insulin hormone binds to the insulin receptor on the surface of cells. So insulin will normally bind and instruct the cell to take up glucose from the blood. But in type 2 diabetes, for some reason, we believe that yes, insulin does bind normally, but the signal is not sent into the cell, and the cells don't take up glucose from the blood, and therefore you have high levels of glucose circulating around, and that causes quite significant organ damage over time. Part one as well is about the inflammatory component. And so it focuses on a particular molecule called the amazone, which is a remarkable structure which assembles inside white blood cells. It originally evolved to protect us from microbial infections, but it's been discovered in latest research to be implicated in a lot of inflammatory type diseases, such as type 2 diabetes, heart disease, arthritis, and possibly even Alzheimer's. So I'd like to say some quick sentences before I show you the animations. I'd like to thank the Water and Life Support Institute for allowing me to be an animator for the last 18 months in their Hello Falls, which was fantastic. I'd like to thank Inspiring Australia for partially funding this project. I'd particularly like to thank the VizbiPlus team, especially Dr. Sean and Jonathan, Christian Salter, and Dr. Kate Paxson for organising this whole project from start to finish. Without them, none of this would have happened, and I'm very grateful for having this opportunity. I'd also particularly like to thank Mark Lawrence. It was a pleasure working with you. You were so busy at the time and really helped to clarify things for me when I didn't quite have the science coalesced in my mind. So it was great working so closely with such a knowledgeable scientist. And lastly, I'd really like to thank Drew for being my mentor over the last 18 months. Just providing such amazing artistic and technical guidance and basically letting me into the world and to learn how to be an animator. It was a privilege and I'm very, very pleased. So thank you. So I'll show you the first animation technique, which is called information capture diversity. Type 2 diabetes, also known as adult onset diabetes, is a metabolic disorder characterized by high blood glucose. Obesity is thought to be the primary cause of type 2 diabetes in people who are genetically predisposed. Thus, overweight people have increased levels of glucose circulating in their blood. The pancreas is an organ which produces hormones that control blood glucose levels. The hormones that control blood glucose are produced by clusters of cells in the pancreas called islets. Here glucose is shown arriving at the islets via the bloodstream. The glucose is taken up by cells in the islet called beta cells. The beta cells respond by producing the hormone insulin, which lowers blood glucose. In type 2 diabetes, high levels of glucose stimulate the beta cells to produce lots of insulin to lower the blood glucose levels. The insulin is taken up by the blood vessels for transport to muscle, liver, and to fat, where it allows those tissues to absorb glucose. Unfortunately, sustained production of insulin also leads to secretion of large amounts of another hormone-like substance by the beta cells. White blood cells, which live in the islet, respond to this hormone and consume it. We are now inside an islet of white blood cells at a magnification of 250,000 times. The hormone, in combination with high glucose, causes production of free radicals inside the white cell. The free radicals activate the sentinel protein that originally evolved to protect us from microbial infections, causing it to unwind. The newly active sentinel proteins then aggregate with 6 other proteins to form a ring. Seven adapted proteins then bind to the ring. The adapted proteins work to capture specialized inactive proteins from the surrounding cell fluid, bringing 2 halves together to form the active whole, which is then released. This entire structure is called the inflammasome, and its sole purpose is to act as a platform for combining and activating these proteins. The newly active proteins then convert yet another small signaling protein, splitting it into its active form. This protein is the key protein involved in inflammation in the body. The inflammatory protein is then secreted from the white blood cells into the islet. Unfortunately, this inflammatory protein causes death of beta cells. Over time, beta cell death causes the islets to shrink, accelerating disease progression. As the islets are now greatly reduced in size, they cannot produce enough insulin to control blood glucose levels. Over time, high blood glucose causes damage to many different tissues throughout the body. What originally evolved as a defense mechanism against infection now seems to be a driving force for inflammation in type 2 diabetes. Chronic diseases associated with inflammation are the most common diseases of aging in the Western world and represent our greatest health threats in the 21st century. Thank you. Now on to the second animation, which is part 2 of the series. And this is the animation focusing on lipolysis. So this is the insulin receptor and type 2 diabetes. Australia is facing an increasing epidemic of type 2 diabetes. There are now approximately 1 million people living with diabetes and around 100,000 new diagnoses each year. Obesity is thought to be the primary cause of type 2 diabetes in people who are genetically predisposed. In part 1, we explained how inflammation in type 2 diabetes destroys the pancreas tissue and dramatically decreases insulin production. Here we describe the insulin receptor in type 2 diabetes.
What we have discovered is the molecular detail of how the hormone insulin binds to its so-called receptor protein on the surface of the cell and instructs that cell to take up glucose from the blood and to store it as an energy source. The receptor itself actually spans the cell membrane, so it has a part outside, a part inside, and insulin binds to the part that is outside. Insulin is a small molecule whose structure was determined a long time ago in 1969. It's been unknown how it interacts with the receptor, and that is what we have discovered. And its interaction are characterized as a molecular handshake as the two proteins dock together. When insulin binds to the outside parts of the receptor, it brings the two halves of the receptor together, and at the same time, the two parts inside of the cell unwind and make contact. These two proteins then activate each other.
This activation allows the insulin signal to enter the cell. Specialized proteins interact with the activated receptor just below the cell's surface. The receptor activates these proteins, and they in turn are able to activate multiple other proteins in a long signal cascade. This complex signaling process eventually tells the cell to take up glucose for use as an energy source. The long signal cascade allows tight control of the signaling process, as it can be turned on or off at many different points along the way. In type 2 diabetes, we believe insulin binds to its receptor normally, but the signal is not sent into the cell and the signal cascade does not develop. This is known as insulin resistance. This means that glucose cannot enter the cell and blood glucose remains high. Over time, high glucose levels damage many different organs.
Insulin, as you know, has been used to treat diabetes for a very long time. But all of those formulations and types of insulin that have been used in the diabetes context have been designed and formulated without any knowledge of the way in which insulin actually interacts with the receptor. And now for the first time, we've got a picture of that, and we can use that into the design of new insulins that could be used for the treatment of diabetes. So we could imagine, for example, the design of insulins that act for a longer period of time, design of insulins that act more quickly, design of insulins that are more stable upon storage, and that's where we like to go with our discovery.
Dr. Bill Wilson, CKD, who's going to talk about time. Thank you.
Hello everyone. Okay, so now I'm going to talk about Alzheimer's. And I haven't prepared any slides because I thought the last thing I want to do is kill you by PowerPoint before you see the great animations here today. So what could I put up there that would compete with these fantastic visualizations of the hidden molecular world? So I'll give a quick introduction to why I'm here and hand over to Chris. So my research team at CSIRO for the past few years has been working with Alzheimer's research. And I guess what is there to say about Alzheimer's? It's pretty confronting in some cases. Most people know someone that's affected. We don't really have any idea on how to delay the onset. But we are getting a pretty good handle on what's happening in the brain, the changes that are going on that cause these physical changes that we observe in people with Alzheimer's. So lucky for us at CSIRO, we've been working together with some really cool people in Australia and world leaders in Alzheimer's research, and together we set up a cohort of researchers. We call it ABLE. And ABLE consists of just over 1,000 really special people that have given up part of their life to actually help us to try and make some advances in understanding this disease and trying to identify something that we can put in place to delay the onset. So this project has had many successes along the way, and it's really spawned a whole industry of research around Alzheimer's. But how do we communicate this? How do we get the message out there? Well, we do what scientists do. We go to meetings, we put up PowerPoint presentations of what we do. We talk to the media about press releases that might link to the publication. Kind of scientists like things. So pretty effective if you're a scientist, but not so effective if you're concerned about your grandmother in a nursing home or what's going to happen to your parents. So when Sean mentioned that I had a chance of actually animating some of this research, what we're doing, it's just such a great way to bring together the work of thousands of molecular biologists and clinicians and carers who are all working on this horrible disease. So I guess over the last couple of months, I've been working with Chris Hammang, who you will meet in just a minute. Chris is extremely enthusiastic, and he grilled me, interviewed me, getting the essence of what Alzheimer's is, what are those changes, what do you actually do? And so this iterative process actually turned Chris into an Alzheimer's researcher. So he's ready to write a review now on the molecular changes in the brain of Alzheimer's and understands the ambiguities and trying to get a simple message across to inform people who are researchers. So making that link between the research, that very abstract world, and informing people is what has been really advising working with Chris on this. So Chris, up you come, my own little Drew Klein, who's going to tell you about the awesomeness of science. Thanks everyone.
Thank you, Bill. I want to say what an amazing pleasure it's been. Unbelievable, the amazing people I've been able to work with. Like Bill Wilson, incredible researcher and really passionate about his work. But also Drew Barry, huge inspiration to me personally. Amazing science communicator, just an incredible resource and a hero for us, especially in Australia. But also to work with Sean Longstreet and Kate Patterson, who initiated the project. It's been an incredible pleasure. And I'm not going to hold you up too much longer. And so I present to you today Alzheimer's Enigma, a video about Alzheimer's disease. Thank you. Alzheimer's disease is a major unsolved puzzle in medical research. Currently, there is no cure, no effective treatment, not even certainty about its cause.
As Alzheimer's disease progresses, brain tissue shrinks and dies. This causes a gradual loss of short-term memory, difficulties thinking, confusion, and behavioural changes, ultimately leading to death. An early sign of the disease is the buildup of plaques around the cells in the brain. For decades, it was unclear what these plaques were made of. We now know they are made from one of your body's own proteins. Plaques develop from this protein, called APP, which occurs on the molecular surface of brain cells. Like all proteins, APP has a use-by date. It needs to be broken down and recycled to keep your cells healthy. To understand how APP is recycled and forms plaques, we need to look inside the cell. Here we see other proteins assembling on the inner surface of the cell, creating a lattice. This structure plucks away a piece of the membrane, forming a package called a vesicle, which contains APP proteins. The lattice disassembles, allowing the vesicle to transport APP to other parts of the cell. The parts of APP that were on the outside of the cell are now on the inside of the vesicle. Vesicles are constantly transporting proteins back and forth between different parts of the cell. This continuous transport is needed so that old or damaged proteins can be broken down and recycled into fresh new proteins, keeping the cells healthy and functional. The first step in this breakdown is done by an enzyme that cuts the part of APP that was previously outside the cell. This leaves a stub of APP embedded in the membrane. A second enzyme cuts the remaining stub, leaving smaller fragments that are then released from the membrane. Normally, these fragments are further broken down, but during Alzheimer's disease, one of the fragments escapes recycling and instead accumulates outside the cell. At higher concentrations, these fragments begin sticking together to form long fibers. The fibers clump together in masses called plaques. The buildup of plaques in the brain can take place over several decades and is one of the main indications of Alzheimer's disease. Plaques can occur years before any loss in brain function is seen. Recently, scientists have identified changes in blood proteins that also occur years before the onset of Alzheimer's. This work has led to new blood tests that can easily and accurately diagnose Alzheimer's disease before symptoms occur. These new diagnostic tests, together with other rapid advances in the life sciences, mean we are closer than ever to solving the century-long enigma of Alzheimer's disease.
Thank you very much. So as you can see, Alzheimer's disease is a very complicated disorder. But we're going to move on now to something a bit lighter. This time, a disease about which we can actually provide you some useful advice that will help you in life. And we're actually talking about food, and we've got microbiome, and a whole number of different stories all along, but I'll let the video do the speaking from that. This one's called The Hungry Microbiome.
We know that many plant foods benefit our health. Scientists now believe one reason for this lies with the gut microbiome, the bacteria in your intestine. Your microbiome is nourished by meals like this, rich in one type of dietary fiber called resistant starch. Resistant starch can't be digested by your body, but instead becomes food for your gut bacteria. Most starch is easily digested. Starch is dissolved in the small intestine and then absorbed by your body, providing you with energy and nutrients. The remaining non-digestible portion is called resistant starch. The resistant starch continues its journey through your gut and arrives at the large intestine. We see that the resistant starch has become exposed to the healthy bacteria of the gut microbiome. This species of bacteria specialize in breaking down the resistant starch. This breakdown process provides the bacteria with the fuel they need to survive. As they use the starch for energy, they release small carbohydrate molecules. The neighboring bacteria feed on these carbohydrates. As the bacteria feed, they excrete even smaller molecules as waste. One of the final waste products is called butyrate, an energy source for your body. As the butyrate builds up, it is absorbed by the large intestine. The presence of butyrate encourages blood to flow into the vessels of the large intestine, keeping the tissue healthy. If your diet includes enough resistant starch, these cells will use butyrate as their main source of energy. Here, we can see the molecular surface of one of the intestinal cells. The surface is covered in special proteins that actively pump butyrate molecules into the cell. Once inside, they can be harvested for energy. In addition, butyrate has other benefits. Intestinal cells are sensitive to DNA damage caused by environmental factors. This cell's DNA has been damaged, resulting in a mutation. More damage could accumulate over time as the cell divides, which could lead to colorectal cancer. But a steady supply of butyrate allows the DNA damage to be more easily detected, and the cell can activate a suicide program in response. Because the damaged cell destroys itself, it can't progress to form a cancer. A starved microbiome is unable to protect you from cancer. By eating foods rich in resistant starch, you can nourish your microbiome and improve your health.
So you've just heard one thing you can do about colon cancer. The next video that I'm here to introduce tackles the topic of pancreatic cancer. And Dr. Kate Patterson, who produced this animation, couldn't be here with us, unfortunately. She's on maternity leave right now. But this was one of the first batch of videos that we produced last year. And just wanted to show that to you as well. So here it comes. This animation is called Cancer is Not One Disease, because it goes on to explain in great detail about the molecular differences between different types of cancer and what we can do about that.
My name's Erica, and in January 2012 I was diagnosed with pancreatic cancer. It's since metastasized into my liver and also a lymph node behind my pancreas.
Every second person will develop cancer in their lifetime. Pancreatic cancer is one of the most aggressive.
One of the things that hasn't changed over the last 30 years is the poor prognosis. So people diagnosed with pancreatic cancer, the 5-year survival rate is only 5%, which is a pretty gloomy outcome for those of us who've been diagnosed with it.
Pancreatic cancer is particularly lethal because by the time it is detected, it's already advanced. That's partly because the pancreas sits in the abdomen very deep and doesn't cause much in the way of symptoms as the cancer develops, and these symptoms are easily confused with general aches and pains.
I think that's one of the hard things about pancreatic cancer is that the symptoms are vague and that they're easily attributed to something else, like stress, irritable bowel syndrome.
Cancers form when normal cells in our body start to divide out of control. Over time, the growing cancer mass destroys nearby healthy cells. Many of the triggers that cause a normal cell to start to divide out of control are found inside the cell, in our DNA. Our DNA encodes the genetic information needed to assemble molecules such as proteins, which are the building blocks of our bodies. DNA is under constant attack from natural chemicals, environmental toxins, and background radiation. Here we can see some toxins shown as bright particles interacting with the DNA and causing the DNA strand to break or causing mutation in the genetic code. Cancer arises through an accumulation of damage to the DNA. In a normal healthy cell, molecules called p53 are activated following damage to the DNA. p53 is part of our natural defense mechanism against cancer. By binding to critical parts of the DNA, p53 molecules help guide the cell's response to the DNA damage. Sometimes the defense mechanism itself can become damaged, and p53 is mutated in over half of human cancers. This means that p53 cannot bind to DNA, and without p53, over a long period of time, cells can accumulate more and more DNA damage, increasing the risk of cancer. Mutated p53 is just one of thousands of molecular mistakes that can occur in cancer. Modern DNA sequencing and other new technologies can now enable these molecular mistakes to be detected in individual cancers. This is important because even though cancers may look the same under the microscope, we now know they can behave very differently depending on their genetic makeup. What's really exciting is that two different types of cancers that look different under the microscope can share some common genetic characteristics. This means that drugs that were developed for one cancer could also be used to treat the other cancer.
I know that they're working on more personalised treatment. It seems that pancreatic cancer has been one of those ones that have been a bit neglected in the past, but it's also a difficult one to deal with. I don't define myself by pancreatic cancer, that's a big thing for me. I feel affronted when the press continues to say that somebody lost their battle with cancer. We're all going to die. Does that mean we're all going to die losers and the press is dying? I don't want to focus on battling cancer. I want to focus on living.
So next I would like to introduce the man who, together with Dr. Kate Patterson and Drew Barry, conceived of this whole project and wrote the grant to Enterprise Australia to get the funding for it, and that is Dr. Sean Donahue. Please welcome.
Thank you very much, and thank you for persisting here this evening. Last year, as we wrapped up the first 3 animations, I had a moment of really a bit of a personal transformation, if you like, related to this project and to myself. Chris was doing the final screen of the Home Microbiome animation, and he sort of turned to me at one point and said, "Guess when the credits is, what was your role?" And I had to think about it, and I thought, maybe I was the producer. And that seemed a bit of a new hat to me to wear because I'm a scientist. I'm not a movie producer. So I am. And that was a step for me. So what I do is, and I spent most of my career is working in what I call the normal science, normal for us. Currently I have 2 roles, one of the government and a joint one also CSIRO, we're working in the health program. The health program also is where Bill Wilson sits, who's featured in the Alzheimer animation. So Olivia is also present in the audience. He's done some imaging games featured from the Alzheimer's animation. And we do a range of other things, including analysis of electronic health records, bioinformatics, and in particular my team focuses on taking scientific data and trying to understand it, and particularly using modern data visualization concepts to make complex knowledge clear. Essentially, I spent my career doing something like this, really looking at macromolecule structures and trying to understand what those structures are telling us about function. This is, of course, the all-time classic example where over 50 years ago now, by understanding the structure of DNA, we understood how life stores, copies, and transmits information. A revelation that has caused the growth of biology ever since. But in the last 50 years, we've been active, and we have now over 100,000 different structures of other kinds of machines, because information storage is just one of the many processes that are happening. And so we have 100,000 structures, and in fact, we can expand that list of structures greatly by modeling. One of the activities of my group, for example, is focusing on organizing all of this information together into a user interface that scientists can use to explore all of those structures and understand and make discoveries. And it's a lot of information. A tool track we released just last week brings together, takes 100,000 experimental structures, models them across a large set of essentially all well-described protein sequences, with this result of about 50 million models. And that interface I just showed you is essentially the way information understanding the matter. So I just want to give you just 2 to 3 slides about where this project came from, its early days. So I'm a tool builder essentially. I try to make these data clear, use data visualization, and about 5 or 6 years ago, a group of us got together and we created an initiative because we realized we've got a big problem in biology. Our data is so complex. To understand it, for scientists to understand their data and to make discoveries from it, this is a huge challenge. And I told you about the structured data. There's lots of other kinds of data, with DNA, RNA, many other forms. So we created an initiative to get all the people that build the tools that biologists use together in a room and to share ideas about how we can use data visualization to enhance this discovery process. And it's been a very successful conference series called VizbiPlus. You may recognize that name. And VizbiPlus really is for scientists like myself. It's not really for the general public. It was initially for. But then in 2011, our second VizbiPlus meeting in Cambridge, Massachusetts, I met this man. He was our keynote speaker. And I still remember his talk to this day. I remember most of the moments of that talk. There were many revelations in that talk to me. And his awards have been mentioned before. What Drew made me aware of was the problem I focus on, which is how we as scientists put this data together and how do we have our light bulb moments. That's one problem. But he's focusing on a different problem, which is having had the light bulb moment, how do we communicate that to the public? Not only make them understand, but maybe make them decide. And of course, this animation approach was just such a brilliant way of doing that. But when I came back to Australia in 2011, we formed this idea to capitalize on Drew's extraordinary world-leading talent in environmental animation and produce this series of animations that you've seen. So the goal was to create 6. There's one missing. Kate Patterson is on maternity leave. Her animation is going to be delayed a few more months. But just want to update you, the 3 animations that we released last year, 101 the first animation for diabetes and Kate's animation was just presented. We actually submitted them to an international competition that's run every year in scientific visualization. This is run by Science Magazine, by the National Science Foundation in the USA. It's quite prestigious, and actually we managed to get 2 of the top 10 positions. that have been announced so far, and 2 of those animations are actually in there. So I think we've already achieved truly world-class results and outcomes from this being. I think this is something I would like to emphasize. In Australia, we really have nothing. We can hold our head up high in this regard, and we should try to continue to maintain this momentum. The results of this are going to be announced in about a month, so really holding your breath to see if we're actually on the very top prizes. Other animations in this area, for example, from major publishing groups, we're up against the ones. So I'd like to invite you, if you're in town in Sydney in June, we've, as part of the series, we've been partnered with the VizbiPlus event in Sydney. It's a really great venue that really embraced the message that we're delivering by making science. We're not going it now, we're just not using jargon, that's not the government country. So we'll have an event there that will feature the final set of 6. And we'll also have as a keynote speaker Gil, who has been the driving force and through various key partners behind the iBook that was presented earlier, the keynote speaker event. So finally, I just have to leave you with this website where all the animations presented today will be available in this presentation, and everything, all information about this whole conference or this whole project can be found there. So with that, I'd like to close the event. Thank you very much for your attention.